This video is a little intro to stoichiometry. It's kind of a weird word. Stoichiometry here. This will be a majority of what we do the rest of the year. You ask old chemistry students what they remember about this class, it's probably this. It's not too terribly difficult. It's got some mole stuff involved in it, but it's fairly easy. So here's what stoichiometry is, just nuts and bolts of it. You have a chemical reaction. So you burn a match, you burn gasoline, you mix two chemicals together, and it's how much stuff was used. So here's our reactants in this reaction. How much stuff did we use? How much did we make? It could be in grams, like how many grams of these two things do we have to use in the reaction? How many grams of this would be made? Or how many moles of these were used? How much was made? So it's all about just how much stuff are we using in a reaction? How much stuff are we making in a reaction? And the numbers out here make a difference in this. So in this reaction, this is saying there's 2 atoms of sodium reacting with 1 atom of sulfur to make 1 molecule of sodium sulfide. That also could mean this. We could say there's, for every 2 moles of Na, there's 1 mole of sulfur atoms, and we make 1 mole of these molecules. So for this reaction to happen perfectly, we need 2 of these for every 1 of these. So if we've got 4 of those, we need 2 of those. If we have 6 of those, we need 3 of those. So this will always be half of that. And likewise, we can say this. If we had 2 moles of sulfur, we're going to make 2 moles of this compound. If 3 moles of sulfur were used in the reaction, we're going to make 3 moles of this because these are in a 1-to-1 ratio. These are in a 2-to-1 ratio. So we're always looking at these ratios in here. So if we look at this reaction over here, I'm not sure my 2 and my 3 are up above. They should be down below, sorry. So those 2s and 3s look a little weird. But for every 2 moles of this compound that react, we produce 4 moles of aluminum and 3 moles of oxygen. So if these were doubled, if this was a 4, we would make 8 moles of aluminum and 6 moles of oxygen. So they're always going to be in that ratio that's in the balanced chemical equation. So as we do some stuff here, one of the things we're going to do is write down these mole ratios. Okay, and we write them as on top and bottom of each other, and they could always be flipped around. So for example here's the mole ratios from this equation. Again, I don't know why the 2 and the 3 are up above. Those should be written down below. For every 2 moles of aluminum oxide that are used in this reaction, there's 3 moles of O2 produced. So that's 1 mole ratio. Okay, that's what we call a mole ratio. Now this ratio could be flipped around. We could say, it's kind of like you say, if there's 3 boys for every 2 girls, there's 2 girls for every 3 boys. So we could flip this around and have 3 O2s over 2 Al2O3s. Another ratio would be for every 2 moles of aluminum oxide that are used in the reaction, there's 4 moles of aluminum produced, 2-to-4 ratio. Same thing as a 1-to-2 ratio. And again, that could be flipped around. And here's our 3rd mole ratio, which can be flipped around. So there would actually be 6 mole ratios we could write in various ways, right? If we look at this equation right here, for every 2 moles of this that are used in the reaction, we make 2 moles of this. So that means if we had 4 moles of that, we'd produce 4 moles of this. If this was 6 moles of HGO, we'd make 6 moles of HG. Another ratio we could say is that for every 2 moles of HG that are made in this reaction, we make 1 mole of O2. That's always going to be a 2-to-1 ratio. So if this was 4 moles made, this would be 2 moles. If this was 100 moles, this would be 50. If this was 1,000, that would be 500. They're always going to be in that 2-to-1 ratio. Okay. We could also do a ratio between this and oxygen, which is a 2-to-1 ratio between those 2 things. So we're always looking at these ratios as we do things. Okay, so we're going to do things right now pretty much in terms of moles. There could be some problems in terms of grams. I'll just throw in a little bit of that, but not a whole lot. So again, I don't know why my document is showing up with the 2s and the 3s up there like that. They should be subscripted and they seem to be superscripted. So on your paper, they should be down below. A little weird that they're up like that. So not a big deal. So if we're doing any problem here, okay, I'm not going to do the problem that's right here first. I'm going to just kind of do something different and say, well, let's say that 4 moles of water are made in this reaction. So 4 moles of that are made in the reaction. If we look at our ratios out in front of those, this is a 1-to-1 ratio. Remember, there's really a 1 out in front of this, a 2 out in front of there, a 1 out in front of here, and a 1 out in front of here. So if 4 moles of water were made in the reaction, 4 moles of that would have also been made in the reaction because they're in a 1-to-1 ratio. Well, this is a 2-to-1 ratio with these things. So if 4 moles of this were made, 8 moles of lithium hydroxide would have been used, and 4 moles of that would have been there. So these are still that 1 to 2 to 1-to-1 ratio. Now, if we end up with some weird numbers, for example, in this problem, it says there's 18.7 moles of CO2. So I'm going to start with that. 18.7 moles of CO2 were made in the reaction. I'm sorry, were not made. Were used in the reaction. Wants to know how many moles of lithium hydroxide would also be used. We're going to write that mole ratio in here, mole to mole. We're going moles of CO2, which has to be in the bottom, to moles of lithium hydroxide. This is where we're coming from. That's where we're going to, mole to mole. And we use the numbers out in front. It's a 1. For every 1 mole of this, there's 2 moles of lithium hydroxide. It's a 1 to 2 ratio. This is double that. So that's all I'm trying to get to. I'm trying to get to moles of this. These labels cancel. I want to finish with moles of lithium hydroxide. I'm done. 18.7 times 2 is 37.4 moles of lithium hydroxide. So we're using this mole ratio. We will use this mole ratio in every single problem. Now, if a problem starts with grams, we have to get into moles, and then we do our mole ratio. We will always do that mole ratio. We're always starting with talking about one thing compared to another in these problems. All right. So let's go here. This one's saying you have 7.2 moles of hydrogen gas that react. So this is 7.2 moles. And it wants to know how many moles of ammonia, how many moles of that. So we're trying to get to moles of that. So we're going from hydrogen to ammonia. So start with the number they give us, 7.2 moles of hydrogen. If we start with moles, we go right to our ratio. We're trying to get from hydrogen to ammonia. And hydrogen needs to go on the bottom, so we go moles of hydrogen on the bottom, going to moles of NH3 on the top. Now, it could have asked us about nitrogen, just happened to ask us about this. It could ask us about anything in there. Our ratio is 3 hydrogens to 2 ammonias. 3 hydrogens to 2 ammonias. Numbers out in front. So ammonia is going to be 2/3 of that. 7.2 times 2. Again, labels should cancel here. 7.2 times 2 divided by 3 is 4.8 moles of NH3. So again, this is our mole ratio step, which gets us from one thing to another in this equation. All right, let's go to another one here. I'll do 2 more of them, I think. I'm going to write this one above it. Number 3, I'm going to do above it because I don't have any room below it because my document's weird. What mass in grams of glucose is produced when 3.65 moles of water react? So this is 3.65 moles of water, and we want to get to grams of glucose over here. Going from moles of water to grams of glucose. So if 3.65 moles of water react with some CO2, how many grams of glucose are made? So start with what they give you. 3.65 moles of water. So I know I need moles of water down below. I don't want grams of water. I want to get to grams of glucose. So I got to get from water to glucose. So now we do our ratio. Okay, and our ratio is 6 waters. For every 6 waters that react, we produce 1 mole of C6H12O6. 1 mole of C6H12O6. So there's our mole ratio. This is 1/6 of that. Well, we want grams of this. So we got to do another step and convert this into grams. So now I'm going to say a mole of glucose, a mole of C6H12O6 is however many grams it is off the periodic table. So look up and see how much a mole is of 6 carbons, 12 hydrogens, 6 oxygens, which is 180 grams in the periodic table of glucose. So we start with moles of water. That's how much water was used. It's a 6-to-1 ratio, 6 to 1. Again, the thing we're going to always goes on top, thing we're coming from goes on bottom. Our label should cancel. And then we say 1 mole equals however many grams is at the periodic table. Remember, multiply 3.65 times 180 divided by 6. Multiply the top, divided by the bottom. And I get about 109 0.5 grams of glucose would be made if we had 3.65 moles of water reacting. All right, I'll do one more question. I'll do number 5. So this one is saying you have 824 grams of NH3, 824 grams of this, and it wants to know how many moles of NO. We want to get to moles of NO. So if we think about this, this is in grams, we got to turn it into moles, do our ratio, which is a 4-to-4 ratio, to get from that to that, and then we're done. That'll put us into moles of this. So start with 824 grams of NH3. I'm going to take grams to moles. It's 17 grams on the periodic table, so I'm adding up nitrogen, which is 14, plus 3 hydrogens. So 17 grams of NH3 is 1 mole. Okay, that's not 4 moles. That's how much 1 mole weighs. So I'm not putting a 4 in there. I'm just converting this into moles. And again, that is NH3 up there. Now I do my ratio, which is a 4-to-4 ratio. For every 4 moles of NH3, there's 4 moles of NO. Again, we could have been going to something else. We could have been going like this to oxygen, then we'd do a 4-to-5 ratio. Or this to water would be a 4-to-6 ratio. This to NO is just a 4-to-4 ratio. So that and that cancel. We're at moles of NO, so we stop. If we wanted grams of NO, we'd do another step and go moles to grams. So multiply across the top, divide by the bottom. Your answer there is 48.5 moles of NO. Now it also wants moles of water. So the only thing we would change if we're doing moles of water is instead of being a 4-to-4 ratio, it'd be a 4-to-6 ratio. We put a 6 up on top of there so you guys can get water. All right, that's a kind of a quick intro, but that'll be stoichiometry. There's another one that's longer. We could do grams to grams. I don't have one of those on this video quite yet.